today we continue to talk about dynamic programming. We will discuss a few more problems which can be solved using dynamic programming. And today I will try to solve some more practical problems, like the problems you actually may face in some of your projects, maybe. Who knows? So the first case is, for example, you want to build a system which makes the difference of two files, like the diff utility, if you don't know how it works. So this standard utility is called diff. It works like this. You have two text files. You have file A and file B. And this utility shows you the difference between the files. It's very useful, for example, when you have something like a version control system. So you have you had some version of this file. Well, let's build some file. So you have some what strings do you have? Let's some random stuff here. Some stuff here. And so on. That's boring. Let's make some real. That's too boring. Let's make something interesting. So let's say you have a program which calculates the sum of elements of the array. So the sum equal to 0, then for I in range, and you do something like s plus equal a of I. Something like that. And then you decided that you only want to calculate what you want to calculate. Let's say you want to change this program to calculate the maximum in your program. So you change this to something like that. I think equal to 0, and then for I in, let's say like minus infinity. I don't know how it's called in. What is the constant for minus infinity in Python? There is no minus infinity in Python, right? Doesn't matter. So you iterate all elements and check if element is greater than s, then s equal to ai. Like this. Float inf. Makes sense. Yeah. So this was the first version, and this is the second version. And you want to find what changes was applied to this program. So what changes do we apply? Let's say we have these lines 1, 2, 3, and 4. Here we have 1, 2, 3, 4, and 6. So which changes should we apply to make this program from this program? We need to change the first line. So first line was changed from s equal to 0 to s equal to float of minus infinity. Then we need to add these two lines here. So we need to add new line 3. So on 3 line we need to add line if I equal to s. And then we need to change this line we need to change line from s plus equal I to s equal Yeah, that's all. Yeah, that's all. Integer min value. You don't have integer min value in Python. In Python, integers are like infinite size. Not a big deal. Something like that. Again, what I want to do? I want to look at two files, this first file and the second file, and produce this list of differences. So I produce like the list of operations which should be applied to this file to produce this file. So how this utility works? It's not that trivial because this utility doesn't have the change log. It only have two versions, version 1 and version 2, and it somehow need to produce the list of operations which should be applied to the first file to produce the second file. So it's not a trivial. So how does it work? It works in the following way, and of course the answer is not unique. There is different way to produce this file from this file. For example, you can just erase all lines from here and add all lines from here. But that's not optimal. So the diff utility tries to produce the minimal possible list of changes. So we want to produce the list of changes which is minimal possible value. So if two files are roughly the same, but you just made some minor changes in different parts of the file, then you will produce something like the short list of changes which should be applied. So how can you do it using dynamic programming? Let's try. First, let's move to the slightly different problem, but it's actually the same problem. We'll talk about Levenstein distance. Let's do the following. Let's have two strings. For example, we have string A and string B. It's always different. I need two words which are roughly the same. Can you suggest me two words? I'm not good in English. Apple and app. Let's do it. Yeah. I like apple, but not app. It's too boring, and it's not exactly the same. It's like they need to be little different, but no, apple and apples. No, these pairs are just too close to each other. Psychology and I even can't pronounce this. Alpine and apple. Nice, thank you. Thanks, Camille. Let's say apple and I. Let's say you have two words, and you want to create again. You want to do roughly the same. You want to make second word from the first word using the minimal number of operations. So what operations can we provide? So we'll have three types of operations. First operation is to change the letter. Second operation is to add a new letter. And the third is to remove the letter. And we want to produce the second word from the third word using the minimal number of operations like this. For example, here what we can do, we can do it like this. So we have this apple. We can, what is the minimal? We can remove this P, change this P with L. Yeah. So we can change this P to L. Then we need to remove this L and to add I and N here. And here we need to add I and N. So we need like 4 operations to get this word from this word. And we change this letter with L, we remove L and add letters I and N here. This minimal number of operation is called the Levenstein distance of the word. Levenstein, like this. I think it's like this. Yes, same as added Levenshtein. Okay. My bad. It is this area, sometimes called edit distance. Yes, it is the same. So sometimes it's a little bit different. Sometimes you have different cost of different operations. Sometimes you have some slightly different set of operations. So we'll fix this set of operations and we will say that the cost is the same for all operations. So we just minimize the total number of operations. Just the simplest version of this task. Okay. Now, how to find the Levenshtein distance between 2 words? It's done like this. Yes. Before I erase this, let's see that our problem is exactly the same. We do the same trick, but instead of individual letters, we here have lines of code. So if you represent each line with separate letter, it will be just the same program. So we have just the same problem. So we have some lines, some list of lines of code, and here we have some another list of lines. If we just replace each line with individual letter, we will have the same problem as here. So yeah, now I can narrate this. How to solve this problem? Let's look. Now you have these 2, so we have 2 words. You have word A, some word A, and some word B. Let's look on the last character of both the strings. So let's look on this character and this character. If they have two same characters in the last position, so we have some character X here and some like this. Then what can we do? We can leave this X in the same place, so we can just leave this X here, so we don't touch it. So this X become this X in this string B. And then we reduced our problem to the following. We need to produce this shorter string like B without last character from this shorter string A. So we need to somehow produce this string from this string. It is the same problem but of smaller size, like we did in the last lecture. So we try to reduce our problem to the same problem but with of the smaller size. So if the last character is the same, then we can leave this character and then have the same problem but of smaller size. So we need to get this string from this string. Now, what happens if the last character is different? Let's see. Okay, here. Let's see. Here we have X, and here we have Y. So the last character is different. Then we actually need to do something. So there should be at least one operation which somehow changes the last character of the string A. So if it was X and in the end it is Y, so we need at least to do at least one operation which do something with this character X. So what are the options? First options is simple. We can change the character. So this applies the first operation. We can change X with Y. So we can make change. So X became Y. And now what we need to do, we do the same. So this X became Y, and now we need to get this again. We need to get this string from this string. So we need to produce this shorter string from this shorter string. And again, we have the same problem of smaller size. The next option is simply, again, we have X here, we have Y here. Next option, what can we do? We can remove character X. So we have character X in the end of the string A. We can remove this character and we'll get some other character in the end of the string. Maybe we need to remove some several times, but if there was X here, but here is not X, maybe we just remove this X, so the end of the string changed. So if we remove this character X, then what we left to do? If we remove this character X, then after this, we somehow need to produce this whole string B from this shorter string A. So, something like that. So we need to produce this whole string from this shorter string A. And again, it is the same problem of smaller size. We reduced this problem to the same problem of the smaller size because we decreased the size of the first string by 1. And the final case, when we have X, here we have Y. What the final option we have is to insert character Y. Insert, add. We can add this character Y here. So we have character X, and in the end we have character Y. So maybe we just inserted the character Y. So let's say add. Good. So if we insert this character Y, then what's left? Before we insert, maybe after inserting, we insert this character Y, we need to produce this string from string A. So we have the whole string A, and we need somehow produce this string B without last character. That's all. That's basically all the options we have. Yeah. If we have one character X here and character Y here, we did one of these three operations. We either change X with Y, we either removed X, or we add character Y. In all these three options, we reduce our problem to smaller problem. So if, for example, if we remove this, then we need to produce this string from this string, and so on. So each time we reduce our problem to some smaller problem of the same type. So the problem is always the same. We need to find the minimal number of operations to get this string from this string. But the size of the problem is decreased. So let's just try to solve all possible subproblems we'll have in this recursion. So each time we remove some characters from the end of the string. So each time the current string A and current string B is some prefix of the initial string A and initial string B. So we will only need to solve the following problems. Let's solve problem D and I and J. We need to find the minimal number of operations to get from string A from 0, let's say, to I minus 1. So we take first I characters of the string A, and we want to produce first j characters of the string B. Good. That's all. Now, we'll try to solve all the problems like this. And by solving, I mean we will use the solution of the smaller problems. For example, what happened here? If the last character is the same, then we may left this character at this place and then create this string from this string. It is the same problem, but of size decreased by 1. So the solution to this problem, the minimal solution, is stored in the array D, I minus 1, J minus 1. Yes, it's two-dimensional array. So like this. Yes. Yes, you may write it like this in most of programming languages, but it's just too complicated for the whiteboard. I'll write it like this. It's two-dimensional array, yes. Here, again, what is the minimal number of operations? We make one operation to change this x to y, plus we need to get this string from this string, and the minimal number of operations to produce this string from this string is again stored in the cell I minus 1, J minus 1. That's all. Now here, if we remove character x, we perform one operation to remove the character, and then we need to get this string from this string. This string has length I minus 1, and this string has length j. And the same here. Here we have one operation plus d of I and j minus 1. So here we have the string of size I. Here we have string of size j minus 1. That's all. So how do we calculate the answer? We just take all the options and get the minimal possible option. Let's write the code. So what will be the code? Let's just iterate. For I from 0 to length of A, for j from 0 to length of b. We need to initialize the border values, because if one of the string is empty, then we don't have this last character. I want to check the last character, and if one of the string is empty, I don't have the last character. So I will check if one of the string is empty, if I equal to 0 or b equal to 0 or j equal to 0. If one of the string is empty, then the number of operations just the length of the string of the, let's say d ij equal to I plus j. Yeah. Okay. It's little bit cheesy, but no, good enough. I'll write it like this. So this is like the base of your dynamic programming. So you need to initialize some base solutions to make next solution use these previous solutions of the smaller problem. So this is the base, basically. If one of the string is empty, then we know the number of operations. Now, if both strings are not empty, then if the last character is the same, I minus 1 equal to b j minus 1, then we just use this formula. Let's see. It's actually not trivial why it is optimal. We may actually use one of these. I believe you can prove that it's always optimal to leave the last character in the place. If the last character is the same, it's always optimal to just leave it. At least if all costs are the same. I'll just leave it. So di minus 1, j minus 1. Else, you need to take minimum of these three options. You just write this. Dij is minimum of these three options. So we have make it like di minus 1, j minus 1, di minus 1, j, and di j minus 1, minus 1, and plus 1. Why is I minus 1? Because I enumerated the characters to y minus 1 here. I use zero indexation, so the characters are enumerated from 0 to I minus 1. Here, I need to check the last character. The last character have index I minus 1. Okay. That's all. That's how we calculate the Levenstein distance. I think in the end I just print the of length of A and length of B. That's the length of the string. I think it's clear enough. I forgot plus 1. I don't need plus 1 here. Here I don't need plus 1 because I don't perform extra operation here. This is the case when we have two same characters here. If we have the same character, we don't need one extra operation. So we get this string from this string and we don't perform operation here. And here I have plus 1 in the end. I get minimum of this plus 1. I just you may write it like minimum of these three functions, but all functions have plus 1, so you can get this plus 1 out of brackets. Like here. That's all. That's how you calculate Levenshtein distance. Let's try it on this example. So in this example, for example, what do we have? We have first string of length 5 and another string of length 6. So we need array like 5 by 6. Oh, wait, plus 1. So we have 6 by 7. Oh no. We have 0, 1, 2, 3, 4, 5 here, and 0, 1, 2, 4, 5, 6 here. So this is array D. Like two-dimensional array. Let's write its letters here just to make it more clear. So we have apple here, and we have open here. And now we simply go row by row and fill this table. Again, each cell of this table contains the result of the solution of the problem for the given prefix of the string A and given prefix of the string J, of the string B. So we take this prefix of string A, this prefix of string B, and calculate the optimal number for these two prefixes. So again, this first row and the first column of the string is pretty simple. So you have just here you have 0, 1, 2, 3, 4, 5, 6. Here again, here you just use this if because one of the string is empty. So it's obviously how to get empty string from the given string is very simple. Just remove all the characters. And if you have empty string and you need to produce this string, you just add all the characters. So these numbers are pretty trivial. And now each time you use this formula again. If you have same character, you use this formula. If you have different characters, use this formula. So go from left to right. You take this cell. You have character A and character A. You have the same characters. So the number of operations is the same as here. So here we have 0 operations. Here you have different characters. You have A here and L here. So how to calculate the minimal number of operations? You need to take minimum of these three solutions, it's this solution, this solution, this solution. In our case, optimal will be this solution. And perform one more operation. We have one. And so on. Each time you take the minimum of these three cases and three options and get the minimal option and put this solution here. Here we have different characters. Here we have 2, 3, 4, 5. Here we have p, it's not equal, so here we have 1. It's not equal here, 1. Here it's equal, so we have character p here and character p. Again, this cell corresponds to the following problem. We have first two characters of string A and first three characters of string B. So we need to find the number of operations to get this string from this string. How to calculate this? We look on the last character, it is the same. So the solution is the same, it's just get string AL from string A. The solution of this problem is 1. So the solution for this problem is also 1. Yeah? So we need one operation. Is clear enough? Hope it's clear enough. And so on. Now each time we take next character. So here we have different characters. So we have 2, 3, 4. Here again we have this p equal to this p. So it will be 2 here, 2 here, and here we have the same character. So here the answer will be same as here, so it will be 1 as well. And so on. Here we have different characters. We have 2, a different character, we have 3, we have 4. And yes, here we have the same character. So here we will have 2. Again, we have minimum. We take minimum of these three options and make plus one operation. So it will be 3 here. Here we have the same character L here and L here. So answer will be the same as this answer. It will be 2. And so on. Here we'll have 2, 3, 3, because here we have 2. Here we have 2. Well, my bad. Here minimum is 1, so it's 2 here, and 3 here, and 4 here, right? Right? What did I miss? I believe it was 4 operations. I need 1, 2, 3, 4 operations. How did I get 3 operations in the end? I need 3 operations. Yes, I cannot remove this L. I can change L to I and then add N. So I need 3 operations. So this program is smarter than me. Okay, so here I will have different characters. So it will be minimum of these 3. It will be 3 plus 1, 4. 3, 3, 3 here, and 3 here. And here I have the same characters E and E. So answer will be the same as here, it will be 3. So that's the final answer. Good. Now, what if you want to actually output the changelog? So you want, if you write a real diff utility, you need to not only find the minimal number of operations, but you want to output the operations themselves. So you don't only want to calculate this number 3, but you want to output 3 operations which produce this string from this string. How can you make this using this table? Again, this is the same basically like we did in the previous lecture. Like when you go from the last state of the dynamic programming, and each time you move back to find the optimal way you achieve this final state of your dynamic programming. For example, here I ended up with value 3 here. How did I get this value 3? Very simple. I had these 2 characters the same, so I obtained this value 3 by going from this cell to here. And how did I obtain this number 3? It's pretty easy. I got from this. For example, you can go from left or from this, from one of these 2 cells. let's say we go from this cell. So we'll go from this cell to this cell, make +1. And how did I get these two? Well, I go from here. And how did I get this one? I have the same characters here, so I just go from here. And here I go from here, and here I go from here. So this is the optimal path to get from this cell to this cell. It means it is the optimal path from the problem when I have two empty strings to the problem when I have two the full strings. And how to find the operations themselves? Well, that's easy. Let's also, when you move through this path, let's find the operations we need to make to make jump from one problem to another problem. What operations? For example, here when we move from these two to these three, we perform operations. So when we move from this is the case when we go from this is this case. So we go from cell ij-1. Here we go from cell ij-1, and we need to perform operation add. So on here we need to add character n, right? And here, when we move from here to here, we need to change L to I. Here, we need to change L to I, and so on. So each time you move from the character, when you perform some operation, again, you look which option did you use, and write the corresponding operation. And here we need to make one more operation, so we need to go from here to here, change P to L. And that's all. Again, so you move from the last state of your dynamic programming using these links. And each time when you move to the previous state and you need to perform some operation to make this thing, you just output this operation. Oh, I try to calculate the minimal number of operations to get from string A to string B. Actually, this formula is symmetrical. If all costs are the same, then it's reversible. So you can use the same program to go from string B to string A. So Levenstein distance is symmetrical. The distance from A to B and from B to A is the same. You can make the same operations by reverse ones. So instead of adding characters, you remove characters and so on. So the distance in both ways is the same in Levenstein distance. But you know, I tried to perform operation from A to B, but you can do the same in the opposite way. Okay. So that's how we calculate Levenstein distance. What is the time complexity? What is the time complexity of this program? No, it's trivial. We have two loops, so total number of operations here is just size of this table is length of A multiplied by length of B. It's quite trivial, yes. Is it good enough for practical use? It depends. If you have short files, like you have two files of say 1,000 lines of code, that's actually usually good enough. So you have 1,000 here, 1,000, like million operations, it's usually good enough. If you have two very big files, like you have two files of each file have a million lines of code, then you have million square is too much. So the actual diff works a little bit differently. So when it has some really big files, it makes some additional heuristics to make it work faster. We'll not discuss it today, I believe, but the idea is pretty much the following. So if you have two big files, but the difference is pretty small, what you may do is to maintain not the whole table, but only the table when the difference is small. So if the difference at some position is too big, you actually don't need this position, because usually it's not optimal. So what you may do is to have this table, but only remember the minimal value in each string and something around it. So You don't build the whole table, but only build the part of this table around the main diagonal, something like that. The answer may, if you have two completely different files of million lines of code, the diff utility will usually not work good enough. So sometimes it's not fine. It does find the optimal way. But if you have two files which are long but they are roughly the same, then usually it will work correctly. So here you have some trade-off between the optimality and time complexity, something like that. Okay, that was the first problem for today. So it's one of the good example of practical use of dynamic programming. So the actual problem when you actually need to perform some dynamic programming solution. Again, it's one of the problem about optimality. It's roughly the same as we discussed in previous lecture when we have like turtle moving from this position to this position. You may find it's about the same, but the cost of moving is a little bit different. So the cost of moving from one cell to another depends on these characters. But the solution is about the same, but the problem is different, but the solution is pretty same. This solution is absolutely correct. So if you can spend this much time, you can solve the problem absolutely correctly. This solution is absolutely correctly. It always finds the minimal possible number of moves, number of operations. Yeah, usually you use diff when files are about the same. So it's like an intended behavior of diff. So if you try to make diff of two files which are completely different, then it might be your problem, not the diff problem. Okay, go. Next problem. Let's look at that problem. Next, we'll talk about text justification problem. What is the problem about? Imagine you have some text processor. So you have some text and you want to put this text on print this text on a A4 sheet or something like that. So I don't want to create some real text. Let's use something. So you have some text. No, I will not use the real text. Let's use it. We only need to have the roughly size of the text, not the real text. The words themselves do not matter. So the only thing that matters is the length of each word. So text can composed of some words, so each word has some length. The length of the word is W, let's say this is W0, this is W1, this is W2, and so on, and -1. So there is text, and we know the width of each word. What we want to do, we want to print this word. These words. So we have this sheet of paper which have width L. And we want to put these words onto this list. So to put them on the list, we need to split them into some lines. So we take the first word, put it here, then the second word, put it here, then we have it here, and so on. Sometimes it may happen that you place the words not optimally, and this ends up you have some big gaps between the words. For example, here, if the next word is too long here, well, let's say this word 0, 1, 2, 3, 4, 5. If the next word is long enough, so it doesn't fit here. So you want to move this word to the next line. Here. So here you will have a big gap. And big gaps between words doesn't look nice. Yeah. So you kind of want all these gaps to be justified evenly. So you want all the gaps to be small usually, because if you have this big gap, it means that the text is not readable, because you need to go from here, then go here, and then the line ends, and then you need to go to the next line, so on. So this doesn't look nice. What you want to do, for example, in this case, you may reassign the words to the lines in different places. So you can move this word 4 to the next line, and this word 2 to the next line. So we have word 0 here, word 1 here, word 2. Do I want to align them to the left or justify by this? It actually doesn't matter. Let's align them to the left, for example. Like this. So move 2 here, and then we have 3 here. Then move 4 here, like 5 here, like this here. In this case, all the gaps are small enough, so we have all these gaps, and we don't have this very big gap. So here we have some very small gaps, and then one very big gap, and here we have 3 gaps of about the same size. Well, cool. So what you want to do? You want to find a way to print the text such that it looks nice. So this looks nice. This doesn't look nice. So this is good, and this is bad. And you want somehow to get good-looking text rather than bad-looking text. And actually, when Donald Fluth was implementing his text processor, he faced a problem like this. So he kind of tries to solve this problem when he was coding his text processor. So how do you solve this? First, we need to decide what does it mean to have good-looking text and what is bad-looking text. So we need to do some measure which allows you to measure how good is your text. It can be done in different ways. One of the ways you can do it is, what do you need to do? You need to somehow explain what does it mean bad-looking text. Yeah? So here for example, we talk that if you have a big gap, it means the text is bad-looking. So we need somehow to measure that if you have a big gap, then you have a big cost of this alignment. So let's say for example that if you have a gap of size x, then the badness of this gap will be equal to x cubed. Let's say x cubed. means that if gap is roughly bigger than usual, then this cost will be increased dramatically. So this is some very so we need some function which is growing fast but not fast enough. So you may put exponential function here. The code will be the same, but here you kind of need to make a good function empirical. So you need to find some, how it's called, some heuristics which will give you the result you need. So this function is actually not from the programming. It's kind of, you need to experiment a little and find the function which works good in your case. In this case, Knut decided that x cube is the good function because it will allow you to make gaps, but the cost of the gaps will be increased fast when you decrease the size of the gap. So it will kind of allow you to big gaps, but the cost will be big for these gaps. What we need to do? What problem we need to solve? We want to solve the following problem. We have this array of words, and we want to put these words on the sheet in such a way that the sum of badnesses of all gaps is minimal possible. And if you solve this problem, you will end up with something looks pretty nice. Okay, it's one of the way how do you solve problems which are not. Sometimes problems which you face are not well how do you call it? Not well formalized. So sometimes you need to find you need to find a good looking text. It's not a formal statement of the problem. So sometimes you need to experiment and find the good formal definition of what is the good function. In this case, we decided that the good-looking text is the text which minimizes this function. It's a sum of cubes of all gaps. Okay, cool. Now, let's see, if we have our text, what we're looking for? We're looking for some split of this array into some segments, and each segment of the text is put on a separate line. For example, here what we're doing, we just put these two words on the first line, then two words on the second line. Line 1, this will be line 2. So we need to split the array of words into some segments, and each segment is placed on a separate line. Now let's calculate, let's make the function which calculates for the given segment the total badness it produces. So if we, for example, let's say we have this array W, and we take all words from L to R minus 1. So if we put all these words in a single line, what will happen? Let's call it bad from L to R. What badness it will produce? No, let's say the length of the line is L. So the gap in the end will be equal to L minus sum of Wi from L to R minus 1 cube, like this. So this is the function which specifies what badness you will produce if you put words from L to R minus 1 on a single line of text. Okay, and you actually you can change it a little bit. It doesn't matter. So, for example, if you want to justify text by width, you will do the following. So if you have this gap not in the end of the text but between the words evenly, So you have all the gaps of the same size. That's another variant. You can do it like this. You can justify the text by the width. So you can say that all gaps have the same width. So what will be the badness in this case? In this case, the badness will be something like, so the total length is L. So we need to have L minus the sum of this. So this is the total size of all gaps. We need to split these gaps into equal size, so divided by the number of gaps. Number of gaps is R minus L minus 1. So this is the size of one gap. We need to put cube and multiply by the number of gaps again. So that's another option. You may use this function instead of this if you want to put text like this. Okay. Cool. Now let's solve the initial problem. So what we need to do, we need to split our array of words into some segments such that the sum of badnesses produced by each segment is minimal possible. So we need to minimize this sum. How can we do it using dynamic programming? Pretty simple. Let's see. So we have this array W. Let's look on the last segment. So let's decide which words will we put on the last line of the text. So we have this last line. If we decided which words will we put on the last line of the text, then we will calculate the badness for this segment, and we will reduce our problem to the following. We need to assign these previous words to some previous lines to minimize the total cost for these previous words. Okay? So we will have the same problem, but again, it will be reduced to smaller size. So again, what we'll do? We need to assign this. We need to split this whole array into some segments and put this segment in separate line. Let's find the last segment. Last segment is just some end of this array. Let's iterate over all possible cases. So let's iterate over the size of this segment. So this segment says size k. Now we need to put these words in a separate line, and then we'll have the same problem but of the smaller size. So we need to assign these words to some previous segments to minimize the total badness of these previous segments. That's all. So how we'll solve this? Let's say, again, we'll have the array D. Let's see, each time we reduce a problem which is some prefix of the array. Yes. So each time we remove some end of this array, so we end up to some prefix of this array. So we will have all the times we have the current state of the dynamic program is some prefix of your whole array W. Let's say Di will be the minimal total badness for words from 0 to I minus 1. Cool. So how do we calculate this? We iterate over the number of words in the last segment. So here we have index I. So this index will be I minus k. So in this case, we need to put this segment on separate line, so it will be bad from I minus k to I. And then plus the minimal cost for this prefix. So it will be plus d of I minus k. And now we simply iterate over all possible values of k and find the minimal option. So it will be minimum of this for all case. And this will be equal to d of n. That's the plan. So how do we solve the problem? We have some prefix of the array w. So this array w. We have some prefix. We need to split this first I words into some segments. We iterate over length of the last segment. Now we need to put this segment on a separate line. It will cost you this. And then we have this problem. We need to split all the previous words into some segments. And the minimal cost is this. Now we take minimum of all possible options. And this will be result for this prefix. That's all. Should we write the code? Let's write the code. It's pretty simple. Do we need to write the code? Okay, let's do it. So I'll write the code and I will do it in a slightly different way. I'll try to calculate this sum, but just to improve the time complexity. I'll try to calculate this sum on the fly. So what's going on? So we iterate from first. Let's say d0 equal to 0. Then we iterate over all I from 1 to n. Then we need to calculate this value d of I. Let's say, again, when we calculate minimum, we just initialize it with plus infinity, and then each time we relax this minimum. Plus infinity, when we iterate over all possible case, so it should be from 1 to I. Yeah, from 1 to. Now I will recalculate this sum. Here we have s equal to 0, here s plus equal, not a, it's w, I minus k. Now this sum is calculated in this variable s. So this badness will be L minus S. So let's say if S is greater than L then break, will not allow to total length of words be bigger than length of the line. And here we just update the minimum. We need d I minus k plus this L minus S. Almost fit. I almost fit it in the whiteboard. Okay. Why is d0 equal to 0? What is d0 again? What is d0? It's the solution of the problem when you have 0 words. If you have 0 words, you don't need to split them. You just do nothing and the total badness will be 0. Again, you may think about this problem like about grasshopper we discussed on the previous lecture. So what actually happens? There's a if you like to think it in these terms, what happens? You stand in this position, and each time you make a jump to the next position. So by making jump, I mean you put some lines or some words in the next line of your text. So, like you're standing here, then you make jump from here to here. And when you make this jump, you actually put these lines or these words in the next line of text. And so on. And so now you assign some costs to each jump. And all you need to do is to jump from here to the end of the array with minimal total cost. So it's done exactly like we did when we discussed the grasshopper problem last time. No, if you have 0 word, you need 0 lines. You don't need a separate empty line to write 0 number of words. That's all. That's how you solve it. Again, if you want to find basically you don't only want to calculate here. I only calculated the minimal total badness, in actual problem you also need to calculate the way to achieve this minimal total badness. So you need to align your text somehow. So what you need is, again, you go from the end, from the final state of your dynamic programming, and each time you go to the previous state of the dynamic programming, which gets you this optimal answer. So you get from here, you get to the left, and each time you get the new line of the text. Yeah, it's not difficult dynamic programming. It's just some more. Today we discuss some more practical dynamical programming. No, it's not difficult. I believe these two problems are pretty much the same difficulty as we discussed on the previous lecture, but they are kind of more practical ones. Okay. I did forget something. Let's talk about time complexity. So what about time complexity here? Here I basically have two loops. So in worst case, time complexity is n squared. But actually it is slightly different, because if you think about this, it's quite practical algorithm, because actually this second loop, each time it adds one new word to the line. So the number of iterations here is no more than the maximal possible number of words in a single line. So number of words in line. So for example, if you have A4 paper and you have like font, I don't know, 12, you may have like up to, I don't know, 50 words in a single line. I don't know exact number, but so actually the number of iterations of this cycle in practical use is pretty small. So it will be n multiplied by this small number. So it's quite practical algorithm, even that in the worst case theoretically it's n squared. It's n squared when if this L is too big. So if this L is big, so the number of iterations here will be too big, and so on. But in practice, this L is usually not very big. So it's just the size of your text or of your sheet. So it's this second cycle, the second loop make some small number of iterations actually. Okay. Do we have time to let's have one more problem. Let's have one more problem. It's a little bit less practical, but it's kind of to illustrate you some more techniques about dynamic programming. Let's talk about early encoding. What is it? It's like usually it's like to do like this. If you have a string, if you have several consecutive actors of the same character, then you can just like if you have string A B. You can change this 3 A's to like something like 3 A's plus B. Yeah, okay. Let's allow to do some more complicated stuff. So let's allow to make it recursive. For example, if you have something like that, let's say A B and then again A B. So let's allow to write it like this. So have 2 times string 3AB. So what if we allow to make constructions like this? What is the minimal possible length of the string? So what is the optimal encoding for the given string? So given string S, what is the minimal size of encoded string? Yeah, it's runtime encoding. Yes, it's not classical. In classical RLE, you don't allow something like this, but in this case, it's more interesting to do it like this. I don't know if maybe they have some names for this. I'm not sure if it's used somewhere. I would not use something like that, but maybe it has some name and it's used somewhere. Not sure about this. Okay, let's get on. But some encoding problems, optimal encoding problems, are widely used. So there are various different types of compressing the data, and so you may sometimes face a problem when you need to find the optimal way to compress your data. So this is one of the simplest. I don't think you will use something like that as a compression algorithm, but yeah, good enough for this. Good enough to show you some techniques. Good. So let's go. What I want to do, I want to solve the problem. I was given a string S, and I want to find the optimal way to compress this string. How can I do it? Again, I will do it using dynamic programming. I will try to reduce my problem to the same problem of the smaller size. How to do it? Imagine you have string S. How can we encode the string S? Let's look on the first character of the string S. This first character, for example, is A. There are two ways. How this character A is encoded. It can be encoded as a single character A. So we can encode the string S as A, plus something which encodes the string S from 1 to n minus 1. 0 to n minus 1. So, how can we encode the string S? We may leave this character A, so we have character A, and then something which encodes the string from 1 to n minus 1. This is the first option. First option is just to leave first character as it is. The second option is to make some repetition like this. So what we can do is to have some string which is repeated several times. Let's have it like this. So we have like k repetitions of the same string. And let's have the length of this string equal to x. So how can we encode this string in this case? We will have something like this. We need to write k repetitions of string as from 0 to x minus 1. This is something which encodes the strings from 0 to x minus 1. And then we need something to, so we need here. First, we need to encode this string, then make k repetitions of this, and then encode this tail. So it will be something which encodes, let's write like this, something which encodes string from s to kx to n minus 1. Yeah. Something like that. So that's all. This is basically two options what we have. Again, first option is just to leave the first character as this, and the second option is to move the first character as a part of some repetitive string. Good. So now each time we reduce our problem to the same problem of the smaller size. In this case, we have this problem for the whole string, and here we have the same problem for this part of the string. And here we have the problem for the whole string, and we reduce it to the same problems. We need to have solve the same problem for this part, and to solve the same problem for this part. So each time, the string we're working on is some substring of initial string S. So each time, each of these problems is some substring of the string S. So what we'll do, we'll solve the problem for all possible substrings of string S. Of L to R will be the minimal encoding for string S from L to, let's say, R minus 1. And now let's solve so first case, we leave the first character as this, and what? Yeah, and solve the same problem here. So in the first case, we have one character here plus solution for the same problem from L plus 1 to R. And the second case, for a given k and x, we need to have we need to find length of k. Let's say we need to length of k plus 2 brackets plus these two recursive calls. So this part will be from L to L plus x, and this part will be from L plus kx to R. Yeah. Also, you need to check that these strings are equal. This can be done using some string algorithms. We'll discuss them next year. It can be done. It's not hard. So you need to check that all these three strings are the same. You can do it using some string algorithms like Knut-Morris-Pratt, Z algorithm, stuff. Yes, next all string algorithms we'll discuss next year in the first semester. That's all. So basically, you do the same thing. You make this two-dimensional array of all the results for your problems for different substrings. And to calculate the optimal result, you get one of these two options. Each time, you also need to iterate over all possible cases and all. So it's not optimal solution actually. It's polynomial but not optimal. And never mind. So you iterate all these solutions and find the minimal possible option. So each time you will get the minimal result. That's all. Two brackets. So I need in this case, I need this number k. I need 2 brackets. So this is 2, and this is k. It maybe change something depending on what details in your program. I don't. You need to specify the details. What cost are for the brackets and what cost are for this number. Good. That's all. Now, two details. First detail is that here I use cell L+1. That's kind of strange, but not what we have before. We usually, here, when we have this regression, we have the L-1, something like that. So this here we have L+1. So to get the solution for this cell, we actually need solution from this cell. So we need to calculate this bottom cell before we calculate this cell of the array. So if this is array, this cell must be calculated before this cell because we use it here. So actually what you need to do is to calculate this array not up to bottom but bottom to up. Well, let's see, here you need to calculate this, and here you need to calculate L. So we need to calculate this cell, and also you need to calculate this cell. This is L, this is R, this is L. No, my bad. L plus X is less than R, right? Let's write it correctly. This is R, this is L plus X, right? This is L plus KX. Not here. Yeah. So if you calculate this cell, what cells do you use? You need to use this cell. You need to use this cell. And you need to use this cell. So you need these three cells to be calculated before your cell. You can do it pretty easily. You just go from bottom to top and from left to right. So when you need to calculate this cell, you already have all these cells calculated. That's the easiest way to do this. Another way to do this is to calculate the cells in diagonal by increasing the size of the segment. So each of these problems is a segment of the smaller size. So you can iterate by the size of the segment. So iterate by increasing R minus L, something like that. That's all. Another detail is what is different in this problem from the problems we discussed before is that when we calculate this state, we use two previous solutions. In all previous problems, we use only one result here. And here we just use two solutions stored in our array to calculate one next solution. So here we have two things. That's the first time when it happened in our lectures. What does it mean? It means that your current state, so this is the state of your dynamic programming, this is like L and R, have two previous states. So when you need to calculate these states, you need to calculate it like two states before. And L plus X, something like that. And when you will try to build the final answer in the end, here I will only calculate the value, the minimal possible value. And if you want to calculate this string itself, how you do it? You do it the same. You start from the end, and each time you try to build the string. And you build the string by making two recursive calls. In previous problem, we make only one recursive call, so we go from the end and use these pointers to maintain the path from the end to the beginning. And here is a little different. Here, to build this optimal string, we need to build optimal string for this substring and optimal string for this substring. So we'll have two recursive calls to build this optimal string, one here and one here. So it's slightly different than before. But the idea is the same. You go from the final state of your dynamic programming, and each time you go to the previous states, trying to build your optimal solution. But here you move not one previous state, but two previous states. And you need to visit them both to build optimal solution here, optimal solution here. That's all. Okay, that's all for today. Thank you for joining me.